Have you ever found yourself, really stuck on a complex decision? Not the kind of thing you just know, but something that really made you stop and think, weigh the pros and cons, maybe even map things out.
Yeah, absolutely. That deep thinking process.
Exactly. That's what psychologists like Daniel Kahneman call System 2 thinking. It's slow. It's deliberate.
Yeah.
Now, compare that to most AI today, especially the big language models. They're amazing at System 1, that fast, intuitive, almost gut reaction stuff, predicting the next word like lightning. But what if AI could actually do that slower, deeper System 2 thinking?
And that right there is the core challenge. And honestly, the huge promise we're diving into today. Current AI is incredible, no doubt, but it often hits a kind of wall.
Right.
When it needs to actually reason through something really new or, a problem with multiple steps, it's more than just statistical prediction at that point.
So that's our mission for this deep dive.
Yeah.
We're going to unpack this pretty groundbreaking new type of AI model. They're called energy-based transformers, or EBTs.
Yep, EBT.
And the key thing here is they're not just like faster versions of what we have. They're designed specifically to let AI engage in that System 2 thinking, learning how to think, just from unsupervised data. No hand-holding.
Which could be huge.
Totally. We're going to explore how this might fundamentally change how AI scales, how it generalizes to stuff it hasn't seen before.
Yeah.
And we've gone through a lot of material for you, detailed papers, background info, expert takes, all boiled down to get you right to the edge of this.
Okay.
So let's really unpack that core problem first. These current AI models, the LLMs everyone talks about, they're absolute masters of System 1, right?
Oh, absolutely. Generating text, translating, making images, incredibly fast. They're essentially predicting the most likely next thing based on, mountains of data they've ingested.
But that speed, that pattern matching superpower, it kind of becomes a weakness, doesn't it? When you need actual, step-by-step, deliberate thought.
That's exactly it. What's fascinating is seeing where that System 1 strength sort of runs out of steam. System 2 thinking that analytical, really effortful reasoning you need for new situations.
Like doing complex math or maybe programming something tricky.
Precisely. That's where current AI often, struggles. And a lot of the attempts we've seen to kind of add System 2 capabilities, they tend to be very specific.
Like only for math or only for code.
Yeah, or just for text. Or they need extra help, like specific human feedback or predefined rules. Even things like reinforcement learning, which is powerful. It might just amplify existing reasoning patterns rather than discovering truly new ways to think. And diffusion models, they iterate, sure, but often need some external check to really deliver on that System 2 promise.
So it always comes back to that core question.
Can AI learn to think deeply by itself without all the extra scaffolding?
Okay, so if the current approaches aren't quite getting there, what's the big shift with EBTs? What lets them do this deep thinking? You mentioned it starts with energy-based models, EBMs.
That's the foundation.
Yeah. And this is where it gets really interesting. You said they don't just predict an answer directly.
No, not directly. Instead, an EBM learns an energy score. And it learns this for, every possible combination of the input and a potential prediction.
Okay. Energy score. What does that mean? Practically. How should I picture that?
Think of it like a landscape, maybe. A hilly landscape, every possible answer, the next word, an image layout, whatever exists somewhere on this landscape.
Got it.
And the energy value is like the height. Lower energy means a better fit, higher compatibility between the input and that potential answer. It's like a ball rolling downhill.
Ah, okay. It wants to find the lowest point, the most stable spot.
Exactly. The most stable, the most correct position in that landscape. So EBTs don't just make a guess. They might start with a rough idea, maybe even just random noise.
Right.
And then they carefully, iteratively refine it by trying to minimize that energy score. Just like a person might carefully think through steps, moving toward the best solution.
That iterative refinement sounds key.
It is. And, connecting this to the bigger picture, Yann LeCun, one of the pioneers in AI.
Oh, yeah, Turing Award winner.
Right. He's been a long-time advocate for EBMs. He sees them as a really crucial path towards truly autonomous machine intelligence.
And why is that? What makes them so promising for autonomy?
Well, a big part of it is that EBMs often work with what are called unnormalized probabilities. Sounds technical, but the key idea.
Yeah, break that down for us.
It basically means they don't have to calculate exact, precise probabilities for everything, which can get incredibly complicated and computationally expensive, especially as things scale up.
Yeah.
Instead, their main job is simpler. Just make sure the tree data, the correct answers, have low energy and everything else. All the wrong answers have high energy.
So push the good stuff down to valleys and push the bad stuff up onto hills.
That's a great way to put it. And skipping that complex probability calculation, that normalization step, gives them huge scalability advantages. It's much more efficient.
Okay, so this energy landscape idea is powerful. How does that actually translate into, thinking in the AI? What does it enable?
It naturally leads to what the research highlights as three really crucial facets of System 2 thinking, things we see in humans.
What's the first one?
The first is dynamic compute allocation.
Dynamic compute.
Meaning, it means the EBT can literally think for longer on harder problems. It does this by performing more of those optimization steps we talked about, more steps trying to minimize the energy.
So it doesn't just have a fixed amount of time or effort for every single problem.
Exactly. It allocates its computational resources based on how difficult the problem seems to be. Just like, you'd spend more time puzzling over a tough question than an easy one. It adapts its effort.
That makes a ton of sense. Okay, so it can spend more time on hard stuff.
Yeah.
What about when the answer isn't obvious? How does it handle uncertainty?
That's the second facet, modeling uncertainty. And this is really neat. EBTs naturally handle uncertainty without needing to compute those exact probabilities we mentioned. That energy scalar, the energy value itself, kind of acts like an unnormalized likelihood. It gives the model a way to express its confidence, or lack thereof.
So, if it's really sure, the energy drops quickly.
Precisely. For an easy prediction, maybe the word "the" in a sentence, the EBT will quickly find a very low energy state. High confidence.
Okay.
But for a harder word, something less predictable, maybe like aardvark or fox, the energy might stay higher, it might not converge as fast or as low. That signals uncertainty.
So it kind of inherently knows what it doesn't know.
In a sense, yeah. Which is incredibly valuable for dealing with the real world, right? Things aren't always clear-cut.
Definitely. Okay, so dynamic compute, modeling uncertainty. What's the third facet?
The third one is prediction verification.
Verification, like checking its own work.
Exactly like checking its work. The energy value itself serves as an explicit verifier. It's a score that basically checks if a potential prediction is good, if it fits, if it's correct according to what the model has learned.
Which is something humans do all the time. We double check.
We do. And what's really powerful here, something the sources emphasize, is that apparently verifying solutions is exponentially easier than generating solutions.
Whoa, okay. Easier to check than to create from scratch.
That's the idea. And it means these internal verifiers built into EBTs can generalize much better. They're better at judging correctness even on new data, stuff the model wasn't explicitly trained on, what researchers call out of distribution or O data.
Which is often where traditional AI models fall down, right?
Yes.
On totally new situations.
That's a major challenge, yeah.
Okay, this idea of built-in verification. That sounds like it could address a big issue we see with current AI, the generative AI paradox.
Ah, yes. Good point.
Where these models can generate amazing text or images, but they don't seem to have basic common sense or discrimination skills about whether their own output is plausible or coherent.
Right. They can generate something that looks real but is actually nonsense.
Yeah. How do EBTs help with that?
Well, EBTs offer a really elegant solution here because the generator and the verifier aren't separate things bolted together. They are intrinsically linked. They're part of the same model.
Ah.
So as the EBT learns how to generate things by finding low energy states, it simultaneously learns how to discriminate between good and bad outputs because that's what the energy represents. This avoids the problems you see when you have a separate generator and verifier that might not be perfectly aligned.
So it's developing that critical judgment as part of its core process.
Exactly. It's a unified approach, which seems much more robust towards actually understanding what it's producing.
Okay, this is all fascinating conceptually. But how are these EBTs actually built? What's the architecture? How do they combine these ideas?
Yeah, good question. Architecturally, they're quite clever. They essentially combine the known strengths of the transformer architecture.
Which we know is great for scaling, handling sequences, parallel processing.
All of that, the parallelizability, the stability, the scalability that made transformers so dominant, they take that foundation and they merge it with the unique capabilities of these energy-based models.
So best of both worlds.
That's the goal. And they come in two main flavors right now. There's a decoder-only EBT, which you can think of as being kind of like GPT, good for generating sequences step by step.
Okay.
And then there's a bidirectional EBT, which is more like BERT, or maybe diffusion transformers. That one's good for tasks where you need to consider context from both directions, like filling in missing words or image patches.
And the training, how do you actually teach it to create that useful energy landscape?
The training process is really key. The goal is to shape that energy landscape so it's smooth and, importantly, convex around the correct answers.
Convex, meaning like a smooth bowl shape. No little dips or bumps to get stuck in.
Exactly. You want a clear path downhill to the lowest energy point, which represents the correct solution. No misleading local minima. Training it this way effectively teaches the EBT to explicitly verify the compatibility between inputs and outputs.
And making sure that process works reliably, making sure the ball always rolls to the bottom of the right bowl. That must require some specific techniques, right? It can't be easy to shape that landscape perfectly.
Oh, absolutely not. It requires some important regularization techniques during training to get that stability and really enable the system to thinking. These were crucial.
Like what? What kind of techniques?
Well, one is using a replay buffer. This basically stores past experiences and helps the model simulate longer thinking trajectories during training, gives it more practice navigating that energy landscape.
Okay, more practice. Makes sense.
Another is using something called Langevin dynamics. This involves injecting a little bit of random noise during the optimization process.
Random noise. Why would you do that?
It sounds counterintuitive, but it encourages the model to explore the landscape more broadly. It helps it jiggle out of those suboptimal local minima. We talked about those little dips where it might get stuck thinking it found the best answer when a better one exists nearby.
Ah, okay. So the noise helps it avoid getting trapped.
Precisely. And finally, they also use randomized gradient descent step size and number of steps, basically varying the exact path the model takes as it rolls downhill during training.
Why vary the path?
It turns out this significantly improves the model's ability to generalize to new situations and makes the whole process more stable. It learns more robust pathways to the solution.
So it's not just the core idea, it's really these careful training methods that make EBTs actually work and exhibit these thinking-like properties.
Very much so. The engineering details are critical.
Okay, let's talk results then, because ideas are great, but do they actually perform? This is where EBTs really start to look like, as you said, a promising new paradigm. What does the data show about how they scale up?
The empirical results are quite compelling. Let's start with learning scalability. This is about how efficiently they learn during training.
Right. How well do they use more data or more compute?
EBTs show significantly faster scaling rates. The papers mention up to 35% faster scaling compared to a standard strong baseline called Transformer++ec. And this holds across all the key ways you can scale. More data, bigger batches, more parameters, more computation, FLOPs, deeper models, wider models.
Wow, across the board.
Across the board. What that really means for you, the listener, is that EBTs seem to be more efficient. They potentially need less data or less computation to reach the same level of performance as other models.
Which is huge, especially as getting more data is becoming a real bottleneck.
Exactly. Data efficiency is becoming critical.
Okay, that's training efficiency. What about when the model is actually running at inference time? Can they really get smarter by thinking longer?
Yes, and that's the other side of the coin, thinking scalability. This happens after training when you're using the model. So EBTs demonstrably improve their performance by as much as 29% on some language tasks, simply by doing more of those optimization or thinking steps, taking more time to refine the answer.
Which standard transformers just can't do, right? They do a fixed forward pass.
Correct. Transformer++ performance doesn't improve if you just run the same input through it again. EBTs actually benefit from that extra computation. They can also self-verify.
How does that work in practice?
You can have the EBT generate several candidate predictions, and then you just pick the one with the lowest energy score, the one the model itself rates as most plausible. It's like asking it to brainstorm and pick its best idea.
Kind of like best of n sampling people sometimes use.
Similar idea, but here the scoring mechanism is inherent to the model via the energy function. And this self-verification leads to really significant performance gains. We're talking improvements going from maybe 4-8% up to 10-14% as the model gets bigger and trained on more data. The benefit itself scales.
That's impressive. And what about handling totally new situations, that O generalization?
Yeah, the out-of-distribution results are also really interesting. EBTs show larger performance improvements on data that's further away from what they were trained on.
So the harder and weirder the problem, the more the thinking helps.
That seems to be the case. It really confirms that this System 2 capability is most valuable for tackling novel scenarios, which lines up perfectly with how we think about human intelligence and problem solving.
Okay, so they learn efficiently, they can think longer to improve, they can check their own work, and they handle novelty better. It really does sound like a different kind of AI. And this isn't just for language, right? You mentioned vision too?
Not at all just language. The results in continuous domains like vision are also pretty striking.
Such as?
Well, for image denoising, cleaning up noisy images, EBTs were shown to actually outperform diffusion transformers, or DITs, which are state-of-the-art for many generative tasks.
Outperform DITs. How?
They achieved better results, and get this, they did it using 99% fewer forward passes.
99% fewer. That's incredibly efficient.
It's a massive difference in computational cost. And qualitatively, the images denoised by EBTs were judged to be less blurry than those from DTs.
Okay, wow. Denoising is one thing. What about understanding images?
There too. EBTs seem to learn significantly better representations of images just through this energy-based training in downstream tasks like standard image classification.
Like telling cats from dogs.
Yeah, that kind of thing. They achieved around 10x higher accuracy compared to DTs trained similarly.
10 times. That's huge.
It really suggests the learned representations are much richer. And even for video prediction, looking ahead frames in a video, EBT showed a scaling rate that was more than 33% faster than the Transformer++ baseline for autoregressive prediction.
So the advantages seem pretty consistent across language, images, video.
The underlying principles seem to generalize very well across different types of data and tasks.
Okay, let's pull back a bit then. How do EBTs really stack up against the models people are more familiar with? Can we summarize the key differences? Let's start with standard transformers like GPT or BERT.
Sure. So traditional transformers, they generally lack that dynamic compute ability. They do a fixed amount of work per token. They also don't inherently model uncertainty in the same way, especially in continuous spaces like images. And crucially, they lack that explicit built-in verification mechanism.
Right. You often need separate models or techniques to judge their output.
Yeah.
What about diffusion models? They're also iterative, like EBTs.
They are iterative, which is a similarity, but a key difference is that diffusion models typically fail to benefit from denoising steps beyond what they were trained on. They're trained for a specific number of steps, and just doing more steps doesn't reliably help.
Unlike EBTs, where more steps means better answers.
Exactly. And diffusion models usually need external verifiers or classifiers to guide them or improve their output for specific tasks. EBTs, you could say, generalize diffusion models by explicitly defining that energy function and having the verification built right in.
Okay. And maybe older models, like RNNs, recurrent neural networks.
RNNs can do iterative computation, that's true. But again, they typically lack those explicit, reliable verification mechanisms that EBTs have with their energy scores.
And finally, what about trying to get System 2 thinking out of current LLMs using prompting techniques?
Yeah.
Like chain of thought.
Yeah, that's an interesting comparison. Chain of thought and similar techniques can definitely elicit more step-by-step reasoning from LLMs. But those approaches are often very problem-specific, right? They work well for math or coding, maybe.
True. And often just for text.
Exactly, modality-specific. And crucially, they often require extra supervision or carefully crafted prompts to work well. The big promise of EBTs is achieving these System 2 capabilities directly from unsupervised learning, potentially across any problem or modality, without needing all that extra guidance.
That unsupervised aspect feels really fundamental. It's learning how to think, not just being prompted to follow steps.
That's the core idea.
Okay, thinking about fundamental differences. This brings us to something really interesting for people deep into LLMs, the reversal curse.
Ah, yeah. That's a fascinating one.
Can you quickly explain what that is for listeners who might not know?
Sure. It's this weird phenomenon where you train a large language model on a statement like, say, George Washington was the first U.S. president. The model learns that association.
Okay. A is B.
Right. But then if you ask it, who was George Washington, it might struggle. Or if you ask, the first U.S. president was who, it might fail to retrieve George Washington. Even though it knows A is B, it doesn't automatically learn B is A.
Which seems like a pretty basic failure of understanding, right?
It points to a potential limitation in how these models store and access information, maybe more like sophisticated pattern matching than true relational understanding.
So how might EBTs potentially address this? You mentioned a hypothesis.
Yeah, this is more speculative, but it's an interesting thought. The hypothesis is that because EBTs make predictions in the input space and during their energy minimization, both A and B tokens are potentially present and being considered in the context.
Ah, so the whole relationship is active during the process.
Potentially, yes. During the gradient updates that shape the energy landscape, the model is evaluating the compatibility of the entire configuration. This might allow it to learn the relationship more symmetrically, overcoming that directional limitation seen in the reversal curse.
So by always evaluating the whole picture, it might inherently learn A is B and B is A simultaneously.
That's the hope. It could lead to a deeper form of comprehension, not just surface-level association. It's definitely an exciting area for future work to explore.
Okay, so wrapping this all up,
Yeah.
what's the big picture takeaway for you, for the listener?
Yeah.
It really feels like EBTs aren't just another incremental step.
I agree. They genuinely seem to represent a potential new paradigm. The core idea is enabling AI to effectively learn to think, to develop these System 2 capabilities through purely unsupervised learning.
And the evidence shows they scale better, both in learning efficiently during training
Right. Better learning scalability.
and in their ability to improve answers by thinking longer at inference time, leading to better generalization, especially on new, tricky problems.
Better thinking, scalability, and generalization, yeah. Plus that inherent ability to verify their own predictions to understand plausibility, it's a much more integrated approach.
So here's something to leave you with, something to mull over. Consider that these EBTs can learn to essentially know what they don't know by expressing uncertainty through that energy value. And they can dynamically adjust their thinking time, putting more effort into harder problems. How might that change the way you actually interact with AI in the future? Are we moving away from just asking an AI for a quick answer like it's a search engine? Could we start maybe collaborating with AI on really complex problems where thought process is more transparent, more adaptable, and AI that can tell you how sure it is, and that can spend more time if the problem demands it? What does that future look like?